Why am I looking at you?
Hello guys, welcome
You're a
back.
picture in a
I
frame.
want to explain
I
about
make believe you're next to me, but I know it's not the
effect of pressure
same.
on the vapor pressure.
Why am I looking at
The
you?
problem of components.
You're a pixel on a screen.
Video.
You're animating principle.
Phase diagram condition. The phase diagram for carbon dioxide shows schematically. This figure, the solid liquid, the line slopes slightly to the right, since V liquid greater than V solid. Note that liquid carbon dioxide is not stable at pressure below 5 atm. For this reason, dry ice is dry under ordinary atmospheric pressure. When carbon dioxide is confined to a cylinder under pressure at 25 degrees Celsius, the diagram shows that if the pressure reaches 67 atm, liquid carbon dioxide will form. Chemical cylinder of carbon dioxide commonly contain liquid and gas in equilibrium. The pressure in the cylinder is about 67 atm at 25 degrees Celsius. 2. The phase diagram for water. For water under moderate pressure, this figure, and the solid liquid lines lean slightly to the left because V liquid smaller than V solid. The triple point is at 0.01 degrees Celsius and 611 Pa. The normal freezing point of water is at 0.0002 degrees Celsius. An increase in pressure decreases the melting point of water. This lower melting point under the pressure exerted by the weight of the skater through the knife that ice skating is possible. This effect, together with the heat developed by friction, combine to produce a lubricating layer of liquid water between the ice and the blade. In this connection, it is interesting to note that if the temperature is too low, the skating is not good. 3. The phase diagram for sulfur. Figure A. Form to solid monoclinic sulfur at 19.5 degrees Celsius above 19.4 degrees Celsius. Monoclinic sulfur is stable until 119 degrees Celsius is reached. Monoclinic sulfur melts at 119 degrees Celsius. Liquid sulfur is stable up to the boiling point 444.6 degrees Celsius. The transformation of one crystalline is often very slow, and if rhombic sulfur is heated quickly to 114 degrees Celsius, it melts. Figure B. The equilibrium as rhombic as liquid is an example of a metastable equilibrium, since the line lies in the region of stability of monoclinic sulfur, shown by dashed lines in figure B. In this region direction, as rhombic, is mono, and as liquid, is mono. What can occur with a decrease in Gibbs energy? In figure A, there are triple points. The equilibrium conditions are at 95.4 degrees Celsius. Mu rhombic equal mu mono equal mu gas. At 119 degrees Celsius, mu mono equal mu liquid equal mu gas. At 151 degrees Celsius, mu rhombic equal mu mono equal mu liquid, where P0 is the vapor pressure at T0 and P is the vapor pressure at T. In section 5.4, this equation was derived in a different way. If P0 equal 1 atm, then 2 is the normal boiling point of the liquid, normal sublimation point of the solid. Then ln P equal delta H per RT0 minus delta H per RT log 0P equal delta H per 2.303 RT0 minus delta H per 2.303 RT. Effect of pressure on the vapor pressure. In the proceeding of the liquid-vapor equilibrium, it was implicitly assumed that the two bases were under the same pressure P. If by some means it is possible to keep the liquid under a pressure P and the vapor under the vapor pressure P, then the vapor pressure depends on P. Suppose that the liquid is confined in the container shown in the space above the liquid. The vapor is confined together with a fluid gas that is insoluble in the liquid. The vapor pressure P plus the pressure of the fluid gas is P. The total pressure exerted and the liquid. As usual, the equilibrium condition is mu vapor Tp equal mu liquid Tp. At constant temperature, this equation implies that P equal V equal Fp. To discover the functional is different with respect to P, keeping T constant. Mu vapor per pressure T P per Pt. This formula, using the fundamental equation, this becomes V vapor P per Pt, V liquid, or P per Pt equal V liquid per V vapor. The Gibbs equation shows that the vapor pressure increases with the total pressure on the liquid. The rate of increase is very small since V liquid is very much less than V vapor. If the vapor behaves ideally, it can be written RT per P dP equal V liquid dP. RT integral P P0 dP per P equal V liquid integral P per P0 dP, where P is the vapor pressure under a pressure when liquid and vapor are under the same pressure P0 the orthobaric pressure. Thus RT ln P per P0 equal V liquid P minus P0. The phase rule. The coexistence of two phases in equilibrium molds the condition mu alpha Tp per mu beta Tp, which means that the two intensive variables ordinarily needed to describe the state of system are no longer independent but are relative because of this relation. On one system, the system has one degree of freedom or is univariant where if only one phase is present, two variables are needed to describe the state and the system has two degrees of freedom or is bivariant. If three phases are present, the relation exists between T and P. Mu alpha Tp equal mu beta Tp. Mu alpha Tp equal mu gamma Tp. These two relations determine T and P completely. No other information is necessary for the description of the state of the system. Such a system is invariant. It has no degrees of freedom. Table 12.1 show the relation between the number of degrees of freedom and the number of phases present for a one-component system. The table suggests a rule relating number of degrees of freedom F to the number of phases P present. F equal 3 minus pressure. Show that the number of phases that can coexist in equilibrium a one-component system is 3. In the sulfur system, for example, it is not possible for rhombic, monoclinic, liquid and gaseous sulfur to coexist in equilibrium one another. Table 12.1 Number of phases present 1, 2, 3. Degrees of freedom 2, 1, 0. We begin by finding the total conceivable number of intensive variables that would be needed to describe the state of the system containing C component and P phases. These are listed in the table 12.2. Each equation that connects this variable implies that one. Table 12.2 kind of variable and total number of variable. Temperature and pressure. Total number of variable is 2. Composition variable in each. Thus, the mole fraction of each component must be specified. The C mole eliminating some of the variable, therefore P enters with a negative sign. The problem of component in a system is defined as the less number of chemically independent species that is required to describe the composition of every base in the system. Example, the system contains the species PCl5, PCl3, Cl2. There are 3 species present but only 2 components because the equilibrium PCl5 equal PCl3 plus Cl2 is established in the system. One can after the number of mole of any two of these chemical individuals. Ability, the alteration in the number of mole of the third species is then fixed by the equilibrium condition Kx equal X PCl3 X Cl2 per X PCl5. Consequently, any two of these